Today, we're going to go back in time, way back. We're heading to the very dawn of artificial intelligence to look at single, really powerful idea that pretty much shaped everything that came after it. We're talking about the perceptron, one of the first, simplest attempts to build a machine that could learn like a human brain. And this is the guy who started it all, Frank Rosenblatt. Back in the 1950s, long before AI was a term anyone really knew, he had this incredibly ambitious goal. He wasn't just trying to build a better calculator. Nope, he was trying to build an electronic brain, based on a fascinating and kind of radical theory of how our own minds might actually work. Because you see, to really get the perceptron, you have to look past all the wires and the circuits. You have to understand the philosophical idea that was driving the whole thing. It was really a theory of how intelligence itself might be born. Rosenblatt's own words here really get to the heart of it. He had this breakthrough realization that you can't just build a thinking machine by focusing on memory. You have to think about what is being learned and how that learning process physically changes the system itself. He wasn't just trying to build a simple pattern recognizer, he was actually trying to model the act of cognition. So he built his whole idea on a few core assumptions that, for the time, were pretty revolutionary. First off, he proposed that a brain's wiring isn't perfectly designed from day one. It's mostly random. Second, he said this network is plastic, meaning it physically changes and adapts as it learns from experience. And third, and this is the big one, he believed that true intelligence could emerge from the simple process of adaptation, instead of having to be painstakingly programmed with a million rules from the top down. All right, so that's the big picture theory of the brain. But how does this electronic brain actually work? Let's dive into the mechanics of how a perceptron actually learns something. It all starts with this little guy, the threshold logic unit, or TLU. The easiest way to think about this is as a super simplified model of a single neuron in your brain. It's the basic fundamental building block of the whole system. And the way it makes a decision is actually pretty simple. It happens in 4 steps. First, the TLU gets some inputs. Think of this as information from the senses. Next, each one of those inputs gets multiplied by something called a weight. Now, this weight is just a number that represents how important that particular input is. Then, the neuron just adds up all of these weighted signals to get a total score. And finally, if that score crosses a certain threshold, the neuron fires and outputs a 1. If it doesn't, it stays quiet and outputs a 0. It's a simple yes or no. Fire or don't fire. That's the whole decision. So you might be asking, where does the learning happen in all this? Well, it's all about those weights. When the perceptron makes a mistake, let's say it sees a cat but calls it a dog, a simple rule kicks in to slightly adjust the weights. If an input helped lead to a wrong answer, its weight might get turned down a bit. If it helped get the right answer, its weight gets turned up. You do this over and over with thousands of examples, and these tiny little adjustments slowly train the network to get better and better. The perceptron was a huge deal. It was a sensation. It really seemed like Rosenblatt had unlocked one of the fundamental secrets of intelligence. But its meteoric rise was about to be met with an incredibly powerful and famous intellectual challenge. You see, as promising as it was, this simple single-layer perceptron had a hidden flaw. And for a while, it was a devastating one. It wasn't a problem with the hardware or even the theory of learning, but with the fundamental mathematics of what it could and couldn't do. So here's the problem in a nutshell. A single-layer perceptron is great at learning how to separate two groups of things, but only if it can do it by drawing a single straight line between them. This is what's known as linear separability. If your categories are all mixed up in a way that needs a curve or more than one line to separate them out, the perceptron is mathematically blind. It just can't solve the puzzle. And this brings us to a famous critique by 2 other pioneers of AI, Marvin Minsky and Seymour Papert. In their 1969 book, Perceptrons, they laid out a mathematical proof of this exact limitation. They showed how even some really simple logic problems, like the classic XOR problem, were completely impossible for a single-layer perceptron to solve. And their argument was powerful. If this architecture can't even handle a basic problem like XOR, how could it ever hope to scale up to the complexities of the real world? The impact of their book was immediate, and it was profound. It was so convincing that funding for this whole connectionist approach to AI, this idea of learning networks, it nearly vanished. It kicked off what a lot of people now call the very first AI winter, a long period where this entire branch of research was basically put on ice. So for years, the idea just lay dormant. But, the story doesn't end there. The core concept of the perceptron, this idea of learning by adjusting connections, it was just too powerful to disappear forever, and eventually, a new generation of researchers would bring it back. Eventually, researchers realized that Minsky and Paper weren't actually wrong about the limitation, but their conclusion was maybe a little incomplete. The flaw they identified wasn't fatal for the entire concept of neural networks. It was only a fatal flaw for that very simple, single-layer version that Rosenblatt had started with. And the solution was actually pretty elegant. Just add more layers. This gave us the multi-layer perceptron, or MLP. The idea is that you stack these simple decision makers on top of each other. So the outputs from the first layer of neurons don't give you the final answer. Instead, they become the inputs for a second layer, and its outputs feed a third, and so on. And this seemingly small change was a complete game changer. A network with multiple layers could now combine all those simple straight lines from each neuron to form complex, curvy, and intricate boundaries. It could finally solve the XOR problem with ease. By going deeper, the network could at last begin to fulfill Rosenblatt's original grand vision of a machine that could learn truly complex patterns from the world around it.
And that brings us more or less to today, because the multi-layer perceptron is the direct ancestor of the massive deep learning networks that power our modern world, everything from your phone's camera to those huge language models. The ghost of Rosenblatt's original idea is very much alive and well.
It's really incredible to go back and read Rosenblatt's words from all the way back in 1958. His goal was never just to build a machine that could sort pictures. It was to uncover the fundamental laws of how information gets organized, whether that's inside a machine or inside a human mind. He was chasing one of the biggest questions you can possibly ask. And that leaves us with a really fascinating question to think about. Are the incredible AI systems we have today just a massively scaled-up version of Rosenblatt's 60-year-old idea? Just more layers, way more data, and a ton more computing power, but still the same core concept? Or, somewhere in all of that complexity, have we actually stumbled upon something fundamentally new about the nature of intelligence itself?